So microphone is in the right spot, no noises.
Yeah.
All good. So welcome again. I hope you had a great day yesterday learning all about AC, and I think it is great to have some experimental demos and tutorials in there as well, because I think you really learn a lot better when you see what's happening rather than when someone is just talking all about it. I don't know if have the devices arrived yet from the DHL? Okay. So still don't have any show and tell for you, but today we'll be talking about 3D printing, and we'll be building on Professor Balraj's lecture last week, and we'll be looking in a lot more detail in what are the printing platforms that would be useful for making microfluidic devices. One of the reasons for doing that is because microfluidics is appears to be a field where you need to have clean room facilities and really expensive instrumentation to make your devices. But with the introduction of 3D printing, we found that actually with relatively affordable 3D printers, you can make your devices with very limited resources. So it's a 3D printing kind of democratizes manufacturing, and with simple printers that are made for use at home, you can actually further your research quite effectively. Of course, if you want to go deeper, then you may need the advanced facilities, but the basic experiments and trying out some designs can be done really well and really effectively by 3D printing. I'm not sure what this slide is doing here. Let's just ignore it. So we've got 3D printing approaches. We've got FDM. Do we remember what FDM stood for? Fuse deposition modeling, which is a printing type where we have a thermoplastic polymer, which is fed through a nozzle with a heater, which means and the heater is heated up above the softening point of the polymer, which means that the polymer comes out of the nozzle as a liquid, and then like a pen, the nozzle can write the molten polymer onto a platform where it solidifies again, and that way you can print. You can do that in layers on top of each other, and that way you end up with a 3D printed device. We've got two photon polymerization, where there is a two-step light process where the first photon activates the laser, and then the second photon initiates the polymerization, all happening together in a small voxel. There is inkjet 3D printing, which is very much like your inkjet printer at home, with that difference that after every print layer, the printed material is cross-linked by the passing of a UV line, UV beam, and then the next layer is deposited on top. So your inkjet printer at home, or maybe here at the university, it deposits the layer on only one layer of ink on your paper. With inkjet 3D printing, it is the same technology. It's a little piezo device that sprays out the ink onto the substrate, but then we can do it in a layer by layer fashion, which means that we can build up device provided we cross-link the layers together with the UV light. And then we've got stereolithography, which has got chemistry which is similar to digital light projection 3D printing, where we use photochemistry to make plastic materials. We have a lot of chemists here in the room, so UV initiated polymerization is a process that's been known for a very long time. You have a radical photo initiator that upon irradiation with light releases radicals, and these radicals initiate the polymerization reaction. With stereolithography, this is done by the writing of a laser beam. With digital light projection, a whole image is projected. And we'll see in more detail, there's different ways of doing that projection. During today's lecture, I'll first start talking about what 3D printing is, what is the process flow to follow one of 3D print devices, go in a little bit more detail on what the different 3D technologies are for a microfluidic. We'll look at what the fluidic performance with types of 3D printing, So which could be better for what application. And we'll finish off with a comparison chart of the different 3D printers and how they compare in terms of cost of the printer, cost throughput, on depending on what you want to do, printer platform you'd like to start off with. In 3D printing, we start off with a CAD model, and we've seen that in Professor Balraj's lecture. He used FreeCAD. There is commercial packages as well as free packages to do CAD drawing. And that CAD model that represents your design. It could be circles, lines, triangles, a complete fluidic network, or a drawing of the doorknob that broke off your door that you want to replace. So sky's the limit, but the CAD model gives the dimensions across the three-dimensional space of what your object that you want to create should be looking like. Wall thickness, all those kind of features need to be thought through. The second step is that the CAD, you upload a CAD model in something that's called slicing software. And what this software does is it creates stereolithography files, which is like you're just slicing the file into little slices. Just like you would do with maybe bread or cakes. This works exactly the same way. On every Z-plane there's a slice made, and then the two-dimensional picture in that slice is stored one after another. These slicing files are then uploaded into the printer, and the printer converts it into G-code, and G-code is the language that instrumentation uses to instruct what to do. So in case of fused deposition modeling, we have the print nozzle coming down, getting out the material at a certain speed, and at the same time our platform moves in the Y direction. So 3D printing, we've got 3 dimensions, we've got X and Y, as well as Z to have our different layers. This movement of the stepper motors is all documented into the G-code, which is uploaded to the printer, and the printer then simply executes. You don't need to know the detail because the printers all have this software in there. So as a user, it is as simple as just upload the file and click start, do your thing, and then click start on the printer. Once we are at the 3D printing process, at the end of the digital light projection one, we'll be talking a little bit about volumetric 3D printing, but by the vast majority we print in a layer by layer manner. So we don't 3D print the whole volume in one go. We print one layer, then we move the stage down or up a little, and then we print the next layer on top. So we make it in kind of 2.5 dimensional layers, one after another. And independent of what the technology is that we use, we ensure that the different layers that we print actually stack together. Once we're done with the layer by layer manufacturing, there may be a need for some post-processing, and post-processing can look very different for different 3D printing techniques. If we've got a liquid resin, we need to find a way to remove that liquid resin from the voids that we've printed. If we do FDM 3D printing, if you remember the lecture that we had from Professor Balraj, and someone has cleaned up here so I can't find the little things anymore, you realize that there were little bits of plastic sometimes poking out that you could remove. That's post-processing. Sometimes you want to use a little bit of a solvent to make it look a little nicer and shinier from the outside. So after the print there may be some work required before you can use the print to its purpose. And after the post-processing you've got your object ready to use. Here we've got an overview again of the different 3D printing technology, moving from FDM, fused deposition modeling, direct writing, where we may be able to deposit material in a liquid. We've got stereolithography, where the beam of a laser is photoclicking a resin. Stereolithography, that is direct. This is the laser writing, this is the digital light projection. So you can see all the, and the binder jetting here is when we've got nylon particles that are glued together where the ink is printed on, and then every layer is put on top of each other, putting a new layer of powder. Wherever the powder is glued together, your object will form. Wherever the powder is not printed on top of the resin, the powder just stays a powder and the object falls apart. And then between the layers you refill the powder. During this course we will not be looking at the metal 3D printing, and as the first 3D printer to look at the detail, we'll be looking at fused deposition modeling. Here we've got the process that I've already talked through in a little bit more detail. You can see that we've got a print nozzle which consists of 2 pulleys that pull the thermoplastic polymer thread into the cavity, where we've got a heater. This heater melts the polymer, which means that a liquid polymer will be coming out of the nozzle and gets deposited onto the plate. Typically we've got the XY stage is moving to deposit the material in the print, whereas the Z stage is moved separately, and that means that the print head may be lifted 100 micron every layer to print the object a little bit higher. The nice thing about FDM is that it is widely adopted for at-home printing, and there's lots of materials commercially available. We've got a broad range of different colors. We can buy carbon-loaded materials that are conducting. We can buy materials that have water-soluble filler in there, which means that if we remove the filler, we can create a porous membrane. There are thermochroic materials, so you could print a cup or a feature that changes color if it's hot. And there's also materials that can be sintered, which means that after the printing you can put it in the furnace and you may be able to convert it to a glass-like material. This is what a 3D printer looks like. It's a box FDM printer about this big, so not a lot larger than a normal printer that you'd be used to. You've seen the box here with the open frame that had a little bit more space in there. And the print head that we've already seen here. It's got the pulley sitting on the top to draw the thread into, and the nozzle sitting here on the bottom where the molten polymer will be coming out. In addition, for 3D the first way that you can use FDM 3D printing is to make templates for casting PDMS. So here we've got a glass plate where the FDM printer, you can see the tip of the nozzle here, has deposited a microfluidic structure, the positive of a microfluidic structure, onto a plate. These structures can then be released from the build plate and put onto another plate. We've got little areas here that we can connect them together, so we can build our fluidic structure from these little modules like Lego bricks. Once we've got the right orientation, we can use PDMS, and we're back at the process that we call soft lithography that we spoke about on Monday. So you can cast the PDMS after degassing over your material, allow it to cure at 65 degrees for 2 hours, and then we can peel the microchannel structure off our template that we'd put on the substrate, and that way we can create the microfluidic structures. This is a little bit more detail on how the fluidic structures, how they fit together, almost like Lego bricks. We've got little socket connectors where we've got a female and a male, and they can be clicked together, and then in the casting process you can actually make complex fluidic devices by just putting your different puzzle pieces together. Here are some examples on how these microfluidic structures look like. They optimize the print processes, so they're because you need to, if you're 3D printing with an FDM printer at too high a temperature, then your plastic is flowing out of your nozzle too quickly, and you get ugly smears like this. If you start, on the other hand, getting too cold, then you get little defects or things are displacing. So there is always an optimum setting, and that setting depends on your material properties, how hot your printer actually goes, as well as some environmental things like humidity. So you may always, with a FDM printer, have to do the little test run to figure out if your settings from last time are still working. But ultimately, if we've got a coin here, we've got the positive structures coming out of the FDM printer sitting here, and then we can print the fluidic structures with that printer afterwards. With direct writing, we have a material that we directly print through the nozzle. So we don't need to, it's a liquid ink that you print in. So with FDM 3D printing, we've got a nozzle that heats and converts the 3D printed material from a thermoplastic that's in the solid state to a thermoplastic that is in the liquid state. With direct writing, we've got an ink that is ready to go, and we can then use this nozzle to deposit the material onto the substrate. There's two different ways of direct writing 3D printing. Either you use a bioprinter, and this is an example of one of the very first 3D printers that I've used, which was used for 3D printing of alginate gels. So it had two different syringes. One of them was direct writing the alginate, the other one was direct writing the calcium solution, and if those two get together, the alginate forms a gel. The box here looks very similar to the box that Professor Balraj showed. So we've got the framework. In this instance here, it was plastic. With Professor Balraj, we had a metal framework. We've got the movement of the nozzle here, in this instance in XY direction, and in this printer the Z stage was controlled here. This printer, we bought it for making microfluidic devices, but it was originally sold for making biscuits. So you can see here that this printer had been used for direct writing cookie dough, and that way it could deposit funny shaped cookies or biscuits, for example, using the shape of someone's letters in someone's name. So with the alginate, it was a two-reagent process. Self-healing polymers can also be squirted through the nozzle and directly written onto the substrate. Another way of direct writing 3D printing is to print immiscible solutions with the same density. At that point, you can put the nozzle into the acceptor reservoir and print in your non-miscible liquid. Because their density matched, your liquid will remain where it is injected in. And here we can see an example where a spiral microfluidic device is being printed inside the solution. See the structure here. If we then can cross-link the accepting solution down, then we actually have a fluidic material that is printed inside the network. And this has been very popular for making fluidic vascular networks for writing these, because in the direct writing process you can change your nozzle across the Z, so you can get really smooth three-dimensional networks being printed. So we will be talking a little bit more detail about cell culture on Friday. So one of our sessions there will be organ on a chip. But other than that, the lectures on 3D printing will not be focusing on 3D printing of biomimetic substrates or organ on chip. We've left that out. We continue to focus on the analytical applications, and therefore we won't be looking at hydrogels. We'll be looking at hard materials. Then we come to SLA, so the first D there should be an S, stereolithography / digital light projection 3D printing, where we use photo cross-linkable resin to use light to selectively cross-link the resin and go from a monomer mixture into a polymer. We can realize that in two different ways. We can realize that by focusing a laser onto our resin, and that way we can write with the laser spot, we can write the features, or we can use a digital mirror device to reflect the light as one area up. The hardware that we have is a Z stage, which can be either moving up, moving down, so you sink the platform into the resin, or in the bed configuration, as we can see displayed here, where you print your 3D printed object onto a platform and you pull your print slowly out of a bath full of resins. We'll be talking about the optimization of the resin formulation a little bit later. And digital light projection 3D printers, they come in a whole wide variety of qualities. In my laboratory, I've got anything between, let's say 50 times 500 is 25,000 rupees is just a consumer print with low resolution. And I've got this expensive printer that is 100 times as expensive, but it can print 2 micron pixels with 5 micron layer height. So we can use that to make really, really small, fine features. Here you can see the price, indeed 15,000 rupees for a printer that you can buy off the shelf. So it's compared to other scientific equipment. Some of these 3D printers are really affordable.
They are commercially available?
Yeah, people use them at home. So you can just get one in the lab, but they are used so that there's people, dentists, well, professionally dentists use them, but people print little parts, so hobbyists print them at home. So these are just Indian websites that I got these models and numbers of. So if you just look for a 3D printer, they are easily available, and it's a rapidly changing market. You can buy the resins. It is very much made for hobbyists. And there's people that like making small figurines, either of, what have I all seen, old soldiers, or so they like scenes at home, and that is the market text, so that people can design their own figurines and then may print them and then paint them in the colors that they want to have. So there's a lot of books on how to use the 3D printer that are aimed at that. So these are aimed for the domestic market. The next approach here is laminate object manufacturing, where we've got like the laminating pouch used to seal paper into plastic. They typically have a glue sitting in the middle, and that is heated up. You can also laminate different sheets of polymer together when you cut the polymer after lamination out into a certain shape. And if you do that, every layer of polymer, you do that cutting out in a slightly different configuration, you can create an object that is being cut to size as you print it, and that's another 3D printing technology. So with laminated object manufacturing, we've got the rollers that feed the new laminate through. Then there's a laser that cuts the laminate to size. And after the end of the 3D printing process, we have a cutting line here that we can remove off. And we've got the 3D printed laminate that we want to leave as a structure there done at the hand. So in addition to doing the cutting with a laser, you can also do that with xerography, what we've seen of making the devices in the double adhesive tape. You can also do the laminate object manufacturing using a dry film photoresist, that instead of using a cutter or a laser to cut it to size, you use photolithography. And the advantage of this that you can go a lot smaller. And in this instance, the dry film photoresist was 5 micron in height, and the photolithography process was also 5 micron accurate. So it ended up with a 5 micron voxel, so it could be used for very precise manufacturing. We're then onto the inkjet manufacturing, which is like your inkjet printer at home. We've got the inkjet nozzle that contains a photosensitive material, and then a piezo-driven device that allows for the deposition of small droplets of inkjet onto the platform. After they've been deposited, a laser or UV light cures the whole layer, the platform is lowered down, and then the next layer is being sprayed on. One of the things is that these printers need to always have the bed full. So we have our materials of our photopolymer that we want to cure and be there. But there also needs to be a support material. So if we have an area that we've inkjetted a material, we also need to inkjet another material in there that we doesn't have a photo crosslinker in there. So it remains a soluble material, but it needs to be there to hold in place. And that is one of the challenges for the use of inkjet printing for making microfluidic channels, because these supports are typically removed by dissolution. Dissolution is easy when you've got turbulent flow, because you just shake it around a bit and all the parts will fall away. If you want to remove your support material out of a 100 micron channel that is 5 centimeter long, that becomes a diffusion driven process, because we don't have turbulent flow. So we need to diffuse our support material out of a 5 micron channel and hope that it will find its way by diffusion to the outlet. So for people that have used inkjet 3D printing for making microfluidic channels, it is not uncommon to have that post-processing step taking 3 or 4 days to clean out the channels again. So a lot of very good ways of making these inkjet 3D printing printed devices, but it is a challenge to remove the support material after you've enclosed the channel as part of the print process. Here we've got a video on how the inkjet 3D printing works. So you can see that the material is deposited. Here we've got the array of nozzles that print the material in place. They're cured by the UV light, and you can see that the print is just putting one layer on top of another. That was too fast, you can see it again. So we've got the print head that prints the material in place. Here you can see a layer of material and the light goes over and it cures. It prints, that's the nozzles, the ink comes out and are cured in place. And part of the nozzles, so you know from your inkjet printer, it can print blue and red ink next to each other. It's using the same concept here, so some of these droplets will be blue ink, and that is sensitive for cross-linking with UV light. The others have the red ink in there, which is the filler material, and therefore doesn't have a UV initiator in there and won't cross-link. So these nozzles that are present, see the nozzle again. Each of those feed heads, see the shower coming past, each of these feed heads creating these droplets is actually connected to another reservoir, and therefore each droplet can have a different material composition in there. There's a range of different photo materials available for the PolyJet printers, but they're all proprietary. So as a chemist, it's rather hard to know the chemical compositions of these resins. And another disadvantage for making microfluidic devices with these printers is that the composition of the polymer may actually change without notification. So if you've got your chemistry established, you want to make sure that you have got a large amount of resin present so that you can continue all your devices from exactly the same material. Typically the resins though are acrylate based because they need to be photo cross-linked. They contain a photo initiator and a photo blocker, a solvent, some other modifiers. There are gel-based support materials as well as wax-based ones. So the great advantage of the PolyJet 3D printing, as I just said, each of these nozzles can contain a different material, which means that you can do multi-material 3D printing. The other great thing about the PolyJet printers, they're actually big machines. The build space is about that big. So if you want to make 100 devices at one time, you can just make them, because our microfluidic devices are typically the size of a microscope slide. So in one print run, we can actually get a decent throughput. The surface finish, particularly on the outside, is really, really nice. So you get very nice looking. If you remember the print from Professor Balraj, you can see the layer by layer process on the outside. The surface finish of inkjet printers printed devices is a lot prettier, nicer and smoother. The other advantage of inkjet 3D printing is a available as a professional service. There's a lot of print shops available. I haven't checked if they're out in India as well, but I know that they are in Australia. We've got multiple in Melbourne. They are widespread in the US. I know that they're present in the Netherlands. So you can just perhaps Google, search on the internet if there is a inkjet or if there is a 3D printing service available in India. And what happens then is that you can send your CAD drawing to that company. You can upload it. It then calculates based on the 3D printing method that you select. It calculates based on the volume how much it's going to cost. So you get a quote based on your custom design, what it costs to print. If you accept the quote and you pay for it, then they print the device for you and they mail it to you. And in our experience, the devices are typically in the order of 50,000 rupees. You've got your own custom print, mail delivered at home. So they're not horrendously expensive. And it means that you don't need to have a very expensive instrument sitting at your university and being maintained at your university. You can outsource your 3D printing, just like if you want to print your PhD thesis and have multiple copies. You may not be doing that on your own printer. You outsource that to a commercial printing service. So there's a number of them available. If you want to have your own inkjet 3D printing, they're an expensive facility to have, and you need an expert to operate it. So the running cost, you need to have a person to help you with all the post-processing, and the materials are rather expensive as well. For microfluidic purposes, the removal of the support material is a particular challenge. The print process, and we'll look at some side profiles later on when we look at the fluidic behavior. The sidewalls can be quite sculpted, and the resolution is limited to 200 microns. So if you need microchannels that are under 200 micron, the technique is simply not suitable. Then we've got 3D printers that are made specifically for inkjet printing of printed circuit boards. So here we've got So that's the nano-dimension dragonfly. Maybe none of you here are in electronics, so it may not be a good way to think about your project if you don't design printed circuit boards and want to rapidly prototype complex multi-layer structures. But maybe if you're working on the synthesis of nanoparticles, all these inks need to come from somewhere as well, and a lot of them are based on nanotechnology. So it may be worth, if you're working on conducting materials or materials that would be in a colloidal suspension, be suitable for sintering, it may be worthwhile to think about applications of research in providing the materials for 3D printing. So binder jetting is when we've got a bed with a polymer particle where we jet a binder or a glue onto the material to then glue the material together in place. Again, movies always tell it a lot better. So the HP multi-jet fusion is a very nice way to do that. Relatively large, but you can make different structures, for example, in materials like nylon. See, I have the pros and cons there. So what the HP multi-fusion does is that the machine applies droplets of fusing and detailing reagents along with some thermal energy, probably through some infrared light, to fuse the powdered material together in a layer by layer manner. Every time a layer has been printed, the powder bed that you saw coming in is lowered a little bit, a new layer of powder is being deposited on top and synced together again. So we've got layers upon layers of nylon powder that are glued together and then molten together during the print process. Once the print is finished, it is hidden in your material. So like treasure hunting in a sandpit or in a big bucket that you may have done as a child, you actually need to dig out your material out of this large container, because every layer the powder has been filled up again. And then you need to remove all the loose powder, which needs to be done with some vacuum cleaners. So the rough material you shake off. Then you need to have a vacuum cleaner to remove the powder material from the smaller spaces. Leftover powder mainly can be reused into the next print. The layer thickness between each layers is 80 microns, but the channel width or the feature width is limited to 500 microns. And that means that maybe for microfluidics the multi-jet fusion is not great. But in my research group we have widely adopted this service because it is really nice to make your holders and the box around your microfluidics. Remember that we talked about, if you work with microfluidics instrumentation, it is not necessarily all about the chip. It is building the whole system around it. Because the powder fusion is relatively economic, it gives a really nice surface finish and a very good dimensional accuracy. If we've got the custom design built, we will quite often use the multi-jet fusion to create the holders to keep all the components and the printed circuit boards in place. Again, the multi-jet fusion, it's an expensive printer. You may not want to have it at your university, but every commercial print entity will have at least one of the multi-jet fusions, because they're so widely used, because the surface finishes are actually really nice, and you can't really tell apart anymore if that these objects are made by 3D printing. Car manufacturers, for example, have adopted this widely to print dashboards. It is a very it's a technology that provides really nice features, good surface finishes, and is very useful if you need custom parts. So we've now spent nearly 45 minutes talking about a whole range of different printers. They've got different minimum feature size, different capital costs, so the instruments have different prices, material availability. Some have a support material, some don't. Post-processing, some of them need a lot of post-processing, some of them don't. Are they open for alteration? Can you change the chemicals? How much can you change the design? Can you use them for print or not? Each printer has got a whole suite of different properties. And there is not the best printer for all applications. So whichever the best printer will be for your application depends on your needs. If you want to use mail order, then high capital cost may not matter, because you're going to print it somewhere else anyway, and that means that the most significant amount that you pay is the material cost and not necessarily capital cost. Whereas if you want to get the printer into your department and you don't have a large budget, you probably want to go to the printers that have been aimed for the at-home market, with that potentially taking a cut in the resolution that you can achieve. So a couple of years now already, we got a lineup of different printers in our laboratory. So we had an FDM printer, PolyJet printer, and a couple of different cost brackets digital light projection printers. So you can see that there is specified XY resolution, which in FDM printing is determined by how thick the nozzle is. With PolyJet printer, it is the number of DPIs, the number of dots per inch that the printer deposits the ink at. With the digital light projection printers, it is the pixel size that are projected onto your screen that determines your resolution. So your resolution between printer types is really hard to directly compare, because the printers use a really different approach to fabricate the devices. Materials, there's either you've got a filament, you've got a photopolymer as well as a support material, or just a photopolymer. And your build area, the space that you can build on, varies significantly from the printers as well, whereas kind of a 25 by 25 is typical for the FDM printers. You can get a lot larger with the inkjet printers, and with the digital light projection printers, your build area is actually relatively small. I thought we were going to go through our performance, but we must be doing that tomorrow then. Okay, so then it's nearly 11, so it's time to see if we've got some tea available, and then during the next lecture we'll be talking in a lot more detail I think we do FDM. No, we do digital light projection first, and then we do FDM 3D printing. So we'll be looking. We've now had the overview of what the different approaches are, and then we'll be looking at more detail at how we can optimize a digital light projection 3D printer to print at the highest resolution that we can. How does the photochemistry work? And the hour after that, before lunch, we'll do exactly the same thing for FDM 3D printing. And then you'll all have the afternoon off, because I'll be moving away to give another lecture somewhere else. And then we'll talk about functional integration and the combination of materials with 3D printing tomorrow. And then we'll be wrapping up with some organ and chip talks. So thank you very much for listening so far. Happy to answer any questions that you still have on the types of 3D printers that are available. There's a lot of information online as well. So if you look at the instrument manufacturers, they're all really happy to talk about how great their printer is. And it is a rapidly moving field. So every 6 months, there's a new generation of printers being launched that are better, higher resolution, faster print speed. So, but I think that the big message to keep in mind is that there's horses for courses. We've got cheap printers that may need some manual work, but that you can do print really nice features with in your lab if you're willing to put some time in understanding how your printer works and optimizing the print processes. If you say, I'm not an engineer, I'm not interested at all in optimizing printers, but I really would like to make the devices that I've designed myself, then you can go to the commercial 3D printers that will have the binder jetting and the inkjet 3D printers. And you can get just your own designs mailed to you without necessarily needing to optimize the print process. So whatever your preferences are, there's plenty of options to start doing something with 3D printing, because in the last decade it has developed incredibly fast, and because it's a technology that is very popular for at-home use, it is very available and we can apply it in our research without really having to understand too much about it. So let's see if there's some tea.
In the meantime, we can start with the
Okay.
We're going to start?
I'm going to start now, and we'll do the break between the digital light projection and the FDM. So
Okay.
it doesn't really matter where we do the break, but we don't want to be eating too much into our lunchtime, waiting for tea now. And we've had a little break now. So digital light projection 3D printing is kind of my sweet spot, my happy place in 3D printing. In a very long time ago, more than 10 years ago, we found one of the very first digital light projection 3D printers available on Kickstarter. Kickstarter is a platform where smart engineers think they've got a good idea, and they're doing crowdfunding to get their product made, and if you supported their crowdfunding efforts, you get one of the earlier products being formed. And that was the start of us in 3D printing. And I should. So we got a Micra 3D printer from Kickstarter. It came into our lab somewhere late 2013, early 2014. We had some intense troubleshooting with the company, but managed to be the first ones in the world to print microfluidic channels. These numbers are old. It's now been cited, I think, around 8,000 times. So I think this by now is my highest citing paper. And here you can see some examples of microfluidic devices that we've printed with this 3D printer. And we found that DLP 3D printing, or 3D printing of devices as such, has got a lot of advantages. If you use traditional microfabrication, we already talked about the chip-to-world interfacing. How are you ever to connect a syringe pump to a flat chip? With 3D printing, you can actually print the threads, which means that your off-the-shelf fittings that you probably have seen yesterday used in HPLC, you can print the threads and use the same fittings to connect to your fluidic channel network on your devices. We demonstrated that we have laminar flow in our printed channels, but we can also make the chaotic mixers that do the Baker's transformation. I still love this photo because it very nicely shows that a three-dimensional network. We've got a microchannel in a plane that comes, splits, one channel goes down, whereas the other channel goes up. And then they combine again in the middle. So it's a split and recombine mixer. And here, using this fluorescent imaging, you can see a green dye and a red dye coming in. Laminar flow, they're separated. And you can see that every step of the Baker's transformation mixer, you can see that the solutions are better mixed. And by the time that we're to our fourth split and recombine mixer, the green and the red fluorescence intensity are actually the same. So we've printed a three-dimensional micro mixer, whereas realizing this structure using traditional fabrication would be at least a 5-layer microfluidic device, and therefore come with a very high failure rate and a high cost in manufacturing. What are the resins made of? They typically have an acrylate in there. In this instance, it's PECDA. We have tried to print in shorter chain diacrylates, but they tend to be really crumbly devices. So it's nice to have PEG as a long chain acrylate because that helps in the structural soundness of the devices that we make. So PECDA is our base resin. It is our molecule that we want to polymerize. We then need a photo initiator, and an example of a photo initiator is ERACure 819. It is a nice photo absorber at around 405 nanometers that most of the printers work. We then have a molecule that we're looking at in more detail, and that are photo absorbers. And that means that we don't get too much activation of our photo initiator at wavelengths that are under our polymerization wavelength, which means that we activate our photo initiator more effectively. And then under here there's some spectra of the commercial resins. The resin chemistry is really important because it provides a couple of features. Resin viscosity, and we don't want a very viscous resin because we know in a microchannel water already behaves like honey. So if water already is so hard to work with as honey, as a liquid in a microchannel, the more viscous our resins are, the harder it will be to drain and vacate them from the voids that we print. So we want to have a resin that is relatively runny, and we want it to be able to print voids. I like this illustration here on how the 3D printing process works. So we've been talking in the overview lecture that we get the light coming in through the bottom, which is controlled through a digital mirror array. So sometimes if we print a feature, a couple of these arrows may not be there because the mirror is deflected in the other direction. We have our different layers that we're printing, and here we've got a build table. So we're now about ready to print our third layer in this instance. So we've had our first layer printed when the build table was sitting between the film and the resin. So we can see a small void of resin. That thin layer was polymerized. This build table was lifted up a little bit, and then the light hit to print the second layer. After that, the print table was lifted up again to print layer number 2. So layer 0, layer 1, layer 2. And we are at the moment that we look at this figure A, we are exposing the light that's sitting in the void between our printed material that's already stuck to our belt plate and our transparent film that separates our resin from our projector. So we've got a small cavity here, the height of which is the layer height of our printer. And if we polymerize the resin that is present here, we form our layer number 3. In B, we can see that we have progressed another few layers. And here we can see that our digital mirror array is no longer projecting the whole build space that we're working in. We have the light switched off for the 2 pixels here, which means that we get cross-linking happening here on the left-hand side. We don't have any cross-linking where we don't have the light on because we have nothing to activate our photo initiator. If our photo initiator is not being activated, we don't have the formation as radicals. If we don't have the formation of radicals, we don't have the formation of former. Again, 3D printing is a lot about engineering, but it is also about chemistry, and this is just photochemistry. No activation of the photo initiator, no polymerization taking place. And then again, the lights are on here, so we have the rest of the pixels is still cross-linking the material. If we do exactly the same thing with the 2 pixels off in number C here, we will have an area where we still got liquid resin present. And if we then print our layer 8 and 9, under there, we again have all our pixels illuminated when we do the printing. 1 second and we'll have our tea. We'll break here. So we can polymerize under our microchannels here. So we can have our design channel still in liquid resin if we have a couple of layers where we do not expose our light. And we'll go into the physics after we've had our tea. think back about what we already know as chemists on doing UV or light absorption spectroscopy. If we've got light falling into a vial and our vial absorbs the light, then the intensity of the light will drop, which is simply Lambert-Beer's law. It is the absorptivity of the components that are in there, and the light intensity, the further you get away from the edge of the cuvette, the lower the intensity is. And what you would do normally when you use the spectrophotometer is that your cuvette may be at a line here, and you measure the absorptivity of your compound in the cell by just measuring the light intensity here. You see that the light intensity has dropped this much, and therefore you can calculate back the absorptivity of the resin. So it's all physics that you already understood for a very long time that we're talking about today. But now we're not using the understanding of what light does when it is in a solution with absorbing compounds. We're not using that for the quantification or the characterization of the compounds. We do that, we start using that to optimize the light dose that we give to the resin in these layers to ensure that we make a polymer, but we don't over polymerize so that we keep our spatial control. So we need to understand our absorptivity of our resin to get the dose just right. Because if the dose is, the light dose that we give is too small, we only get some oligomers being formed, we don't have a cross-linked network, and if we move our stage, we just get the oligomers staying suspended or dissolved in the resin, and we don't have a feature formed. Whereas if we expose too much, we lose our spatial resolution. So we just need to get a just right point. And therefore we need to go through a little bit of physics where we define what the layer height, what the thickness is that our resin will polymerize based on the intensity of the light that we're putting in and the absorptive properties of the resin. And we've already seen on the first slide, if we look at different ingredients of a resin, we've got the monomer, we've got the photoinitiator, we probably have got some photoabsorbers in there. All of these compounds are chemicals and therefore will have their own absorption spectrum. So we need to know at the light intensity what the contribution is of all of these compounds to the overall absorption of our resin. And those together make this curve. And we've got a parameter called HA, which is the minimum layer height that can be represented with this resin. This number has been picked to the fact that most polymers, if you have 1/E, so about 37% of the original intensity, that is when a polymer has gone to cross-linking enough that if you remove the substrate from the build plates, there is actually a gel-like substance still there and it doesn't wash away yet. So just pragmatically decided that if it drops to 1/E, that is the point where we've got enough gelification, enough cross-linking within our forming material to have a true object being formed. It doesn't wash away anymore. We have all the edges, we've got them there. And then we can calculate what the light intensity is at that distance away from our edge. So the light dose that the resin receives is the product of the light intensity that's coming in and the time we allow for that exposure to go ahead. We then have something that's called the critical light dose, and that is the dose at which the polymerization has exceeded to far enough to get to a gel-like or nearly solid material. So that is when we have polymerized our resin to the height of HA. For a specific resin, the TP is the time that it takes to reach the critical dose at that certain Z length. So the time that we have defined here that the light dose is the product of the intensity and the time. We know that we need to get to a certain amount of light. We know how much our resin absorbs. Therefore, our light dose becomes a function of time. And the time TP is then the time that it takes to get our minimum layer thickness to get that formed. So to print structures with high resolution, getting that critical dose known and setting your exposure time to the point that this critical dose is met is critical. Because if you don't have your exposure set well, either you don't have an object or you get... Yeah, we've got our wasp again. Off you. Or you get overexposure, which means that your features that you're printing are unnecessarily bulging out. To compare things, the engineers like normalizing different factors, and here the normalized exposure time is defined. So if we've got different resins with different absorptivity, with different composition, the minimum layer height will be different. So we can see that if we've got our exposure time, or in this case our normalized exposure time, and the polymerization depth, the slope of this depends on the absorptivity of our resin, which in turn dictates the thickness of our layer HA.
Can you go to previous slide? Polymerization depth? No. Next one. Yeah, this one.
Yes, so the HA, the polymerization, so here we've got the polymerization depth. That is, if you expose for a certain amount of time, you form this much polymer. If you expose for longer, you form more polymer because your light dose goes up. The rate at which this goes up is your penetration depth. So the depth of polymerization, how thick our layer is that we print, relies on the dose that we print, using different functions depending on our HA, depending on the absorptivity of our resin. And that is then also interlinked with the optimized exposure time. So we've got different conditions here where we've got resins, and on the next slide we'll talk about how we can actually, once we've got a resin mixed up, we can through simple experimentation, we can determine the HA of our resin, which then allows us to also derive our optimal exposure time. Why would we be doing all of that? Practically, what we really want to print is small features without a lot of backscattering. So here we've got little posts that are printed in a layer-by-layer process. Here we've got a scale bar of 100 microns, so these are about 200 micron in width. But here we can see a suspended bridge. And this suspended bridge in this instance is only 10 micrometers high. So we've got a bridge that's formed. So the light dose that we've given here has been enough to cross-link the resin, but we don't have any bulging out of the material here. So we've got the bridge that's interconnecting, but only at 10 micron high. If we wouldn't have optimized our dose, either this bridge would not be existing, it wouldn't be connecting, or it would be bulging out and being thicker than it was designed to be. So the reason that we need to understand what the absorptivity and what the optimal dose is for our resin is because in microfluidics we're really finicky and we want to print these really fine features. And this is the practical part of using all these physics. Once we've got a 3D printer and either we've got a resin that we've bought commercially, we've bought a couple of resins through Amazon, that because it's adopted at the end-home market, there's a whole wide range of different resins in different colors or with different properties commercially available. Once you've got a new material coming into your lab, you can change the layer exposure time with your printer. That's one of the print settings that once you set up your printer, you ask it to expose each layer for a certain amount of time. So that is the parameter that you can vary in the lab. If you then have a structure like this, you print this structure over and over again, but with increasing exposure times. Then with either a microscope or some calipers, you measure the thickness of this bridge. for each exposure time, you measure the thickness. So here for the resin that contained 0.05% of Sudan 1 as a photoabsorber to kind of minimize, control that layer height. A range of different exposure times were set in the printer, and at the lowest exposure time, the layer height measured was about 50 micron, probably 55, 70, 75, and 100. Whereas for another resin, Plus Clear is a commercially available resin, you can see here that at we needed higher exposure times, but again we can measure the thickness of the membrane that formed at those different exposure times. And here for the Plus Clear resin, the fact that we don't have data points probably means that at any lower exposure times we didn't get any polymer formed, so there was no bridge here being formed. So the physics underpinning it, I just talked you through it. It works, it is all underpinned by first principles. If you go into 3D printing, this process is actually all that you need to understand. So you can trust the physics behind it. You can then determine the exposure time for a layer thickness Z by increasing the exposure time, measure the layer thickness, plotting it. Please note that this is a logarithmic scale. And then once you've done that, the slope here of this line, the fitted line, is your HA. It is your minimum exposure thickness. And TC, your critical exposure time, is the intercept with the x-axis. So you can extend the line and then calculate your minimum exposure line time for this resin. Getting back to the fact that we want to print voids. So we want to here be able to not expose a certain area because we want to print the voids. And we want to be able to, after we've taken the pick out of the printer, we want to be able to wash out the resin so we are left with a small void. There is more happening because unfortunately our exposure doesn't stop at our layer height. Our exposure, we've seen in all of our graphs, is an exponential decay. We've set our HA at the cutoff point of 37% of the intensity. Unfortunately, that means that there's still 30% of our intensity left at the other side of our layer. So if we look at the dose that a certain layer receives when the second layer is being printed, it increases. So we've got our layer number 0 also receives a small light dose when layer number 1 is being printed. It receives more light when layer number 2 is printed. It receives more light when layer number 3 is printed. So every layer that is printed below, the extra dose that's added up is higher because we're further away. But it is important to note that the light dose that your layer receives is not only the light dose when your printed object is being printed. When we are exposing the next layers here, the light that is coming here is penetrating through the different layers and still hitting this void. So the challenge with optimizing the resin, optimizing your settings, is to ensure that the light dose that this channel here still receives by printing what's sitting underneath is below the point that this forms a material that is too cross-linked, too far oligomerized to still be able to be removed. Unfortunately, we can't stop the transmittability of the material while we are printing. So if here is still is being printed, the void here still receives 37% of the dose because that's how we defined our optimal exposure time. And that's the intensity we need to go from loose oligomers to the gel state. So it is not a digital process as such. We will have the light still penetrating, and you can see here that the first printed layer receives a higher light dose than the less printed layer. So here we've got the layers being printed. When this layer is coming in, there will still, it is inevitable that there will still a little bit of light be coming in. And one of the ways that so we've got oligomers being formed and we don't want them to become gelled. So there is ways of calculating how that works, and you can calculate what you can do to minimize the exposure. And quite practically, what we do in our lab is that we reduce the exposure time in this layer that sits underneath by a little bit, so that we minimize the extra dose that this layer receives here. So here we've got a graph that we're printing a channel, and you can see here, even though the layer has not been given any exposure, but through the sum of the exposures coming from the layers printed afterwards, there will be still a little bit of oligomers being formed when printing a void in layers 5 and 6. One of the ways that you can minimize that exposure, and you've heard me talk already about the fact that we don't only have a photopolymer in the mixture, but also a photoabsorber. And the photoabsorber is a highly absorbing compound that allows you to contain that light within your polymerization mixture by just being a very strong absorber at that wavelength. So what was published in that paper, and it's really a really nice resource, it looked at a whole range of commercially available dyes, measured their spectra, characterized if they were soluble in PECTA, which is the most frequently used diacrylate for resins that are blended in-house, measured the spectrum, did some polymerization, determined at the used printer settings the HA and the TC, and then looked to see if there were any influences of the material strength, was the final chip autofluorescence or not, and could small channels be printed. And then they selected for their printer one of the dyes, but if you've got another printer, your outcome out of this list may very well be another dye, but a lot of the spectra and the information that are given in this paper provide a really good guide that if you want to start developing your own resins, what photoabsorbers could you use to increase the absorptivity of your resin, and therefore to minimize that carry forward of the dose from the layers printed afterwards in the layers where you want to have your voids. Here we've got the spectra. So these are the spectra of the different compounds. You can see here overlaid with the this is even the 380, with the 380 output of the printer that they were using at the time. A lot of the commercially available printers for at-home use, they use a high-intensity light source at 405. So you may want to have to, if you want to repeat this, understand the spectral properties of your own light source, and then maybe even look at other dyes, even though here there seems to be one that's very good absorptivity at 4 or 5 nanometers. You can then determine what the dose is for different Z layers, for different layer heights, and you can determine the HAs by experimentally varying your exposure time and using where's the bridge structure? Too many things in there. Using that bridge structure to determine how thick the layer is when you print at different times. So this is, it takes 1 or 2 days in the lab because you need to continuously get your prints in and out. But it is not a hard thing to do, and it provides you with great insight on where should the optimal exposure time be to work with my resin. And after doing all of that, you get really, really nice channels. So here we've got a couple of different exposure times, 200, 400, 600 milliseconds per layer. Here we've got devices that are having 2 pixels wide, and you can see in 3 layers we get very nice fine microfluidic channels being formed, where we get channels that are each layer is about 8 micron thick, which means that in 3 layers our microchannels are 25 micron high. So these are really fine microchannels, and by you picking the right photoabsorber, the light penetration, the oligomerization in these microchannels could be limited to the point that 10 centimeter channels could be easily flushed out. What that then allows you to do is actually print really complicated fluidic networks that allow you to do great fluidic control. We've already talked about fluidic control, about valving. Here we've got used the flexibility of this really thin printed membrane. Remember, we've cut back the A, it is a long polymer, it is a little bit soft. So what was found is that you could actually use this to make a thin freestanding membrane that then could be used to, if you apply pressure, close down the intercontact between two microchannels and stop the flow. Whereas if no pressure was applied, we could get flow from this channel through this intersection into the other. So applying a little bit of pneumatic pressure. Remember, we've talked about the quake valves, we've talked about how we could use PDMS to balloon and valve. These very thin printed 3D materials, they are flexible enough that you can use the same valving proposed in the quake valves, but then inside a 3D printed device. So we apply pneumatic pressure, we can close a valve. We talked about the quake valve, that one of these features is nice. But what if we have multiple in parallel? With the quake valve, that was a way to create a pump. So here that is replicated with a microfluidic device. We've got 3 different of these valves in series, which means that if we sequentially open and close these valves, we can create a peristaltic pump using a 3D printed fluidic network. Would be relatively complex at this size to create with any other manufacturing methods, but being able to print these sub 100 micrometer channels actually allows you to end up with really complex geometries, have valves in there, and have a pneumatically controlled liquid pump where we can, from our inlet channel, we can open this valve, which means that the liquid can go to the next one. Again, open that valve to allow to move through, open this valve, move that way. So we've got different control channel lines. This is where the pressure is applied to actuate the red valve here. C goes here around the back to control and move this valve down. And then we've got a third valve. How that looks in reality. Complex, scary, but it can be made. Look at the scale bar here. This is 1 millimeter. Very, very small. We've got our control lines C1, C2 and C3 to apply the pressure above our valves 1, 2 and 3. We've got our inlet channel and our outlet channel. So we're going, this picture here is put in the opposite direction as the schematic that we just had. But we've got the liquid coming in, can be pumped through, and then we can close valve number 1 by activating control channel 1. Control channel 2 was the one that goes through the back, and control channel 3 then goes, valve number 3 sits here. So control channel 2 produces this one, and then control channel 3 goes there to the bottom. Here we've got a picture from the side where we can see the valves, the membranes, and the microchannels. All 3D printed, and this in here is 500 micron. So this is less than a millimeter in diameter to have our fluidic valve that can work as a pump. So if we can do 3 with 3D printing, CAD drawing is easy to make. We can do 6, and here we can see that we can fluidically control the movement of a red and a black dye through the microfluidic device simply through pneumatic actuation of the different valves that we've printed. So we need to have a pressure source, some relays to switch on and off the pressure to these air channels, and then we can control at a femtoliter volume the fluids that are moving inside our microchannels. So here we can see that we've got our different valves, and then we'll see them actuating and pumping the liquids around. So number 2 is being activated. You can see that it's going, switching on and off, it's moving up and down with the frequency dictated, and you can see that the red dye is being pumped. And then in a little bit our valve 5 is being activated, and we can see that the black dye is printed into its direction. it is not smooth flow, it is a peristaltic pump, it is a moving part, so we pump a little bit at a time. But you can see that by sequentially actuating these valves, we do have little pumps, and we can close some of the channels out and some of the others in. Again, keep in mind that this is a millimeter and realize how small a millimeter is. So we can go through the fluidic sequence where different valves are activated or closed. We can pump liquids, we can create pressures, and we can have very high level control at picoliter volumes. I thought we were going to, yeah. So there we've got the red one activated again, and we've now got the red dye directed so that it's going into the channel. This is a nice illustration of technology, but imagine if you want to do an immunoassay where you want to load your sample, you want to have the binding, you want to wash it away and then add your fluorescent antibody to do your ELISA. At that point you need to have 3 different fluids that you pump over your reagents, and having a way to control those fluids at a small scale means that you can get to functional integration. The plumbing is hard. How do you interface that with the exterior world? I talked before that in the very first paper that we did the 3D printing, we could interface with the standard HPLC fittings. If you improve the resolution in 3D printing and you go to the small channels that I've shown here, then all of a sudden an HPLC fitting becomes massive. They're the finger tights, they are about 1 centimeter in diameter. You would need to have such a much larger chip to use those fittings that that's no longer possible. So here, what they did was that they created a fluidic interconnect that had small taper channels that you could connect or push, almost push fittings, to push your tubing in from the side to allow the delivery of different fluids. And then there were little indents made in the bottom that would interface with the microfluidic chip. So they printed one device that had the input for the different tubings and then the outlet to connect to the small microfluidic device. Then they could change the layouts of the microfluidic device without having to worry about the fluidic interfacing, because every chip that they designed would have this geometry in here that fitted it together again and allowed for the interfacing. Here you can see that there's a couple of different chips where they looked at over different times what the pressures were they could apply without the instrument breaking down. You can see that there's an array with all these interfaces for the liquid interfacing, and they all continue to work. So this array of having the an interface between the pumps and the devices worked really nicely, and it shows that sometimes modularity is really important. Because one of the things that I haven't said yet, that if you go higher and higher in resolution with printing, you significantly increase your print times. If you've got a cheap printer and you've got 5 micron layer height, that takes 5 seconds exposure each. If you then want to print 5 layers, you print them, so 500 micron layer height. If you want to print something that's 2.5 millimeter high, that's 25 seconds, 5 times 5. If you change that down from 500 micron to 50, then all of a sudden you need to print 10 times the amount of layers, because each layer is thinner. Which means instead of 25 seconds, you have to print for 250 seconds. So the smaller layer height, the longer it takes for your print to run. Which means that if you want to print really fine microfluidics, the fastest is if you can print a really thin chip and then have your fluidic interfacing, which typically does take your size, your height in Z, have that realized with another interface that you can use on different devices, because that simply enhances the throughput of the number of experiments that you can conduct in the laboratory. So that is high resolution printing of polymer. If we go to the first lecture on microfabrication, glass is the dream of most chemists because glass is inert. Could we also print in glass? And the answer here is yes. You can do photo cross-linking of very overloaded colloidal suspension of silica particles. In this instance, the RAP group found out if that you get 3 different sizes of silica particles, they can actually pack in a solution that only has got 5% solvent in there to a really close colloidal suspension. But because they're all nanoparticles, it is still a reasonably low viscosity fluid. So you can use the digital light projection process to print so-called green parts. So you have the 5% of liquid contains your photo crosslinker, and you can cross-link these colloidal particles in place using the digital light projection printing that was also used for the device that we talked about so far. This device can then be put in an oven to evaporate off the 5% of solvent and burn away your polymer that holds all the colloidal particles together at the same time as your 3 different sizes of silica particles thermally fuse together. And here you can see the results, a 3D printed sintered glass device. So you can get the geometric accuracy using digital light projection printing. Your green part still contains about 5% of organics, but using the sintering process, you can remove these organics and you end up with a nice glass part with detail that I wouldn't know with which other techniques you could make these kind of glass devices. So here we've got the monomer, our silica particles, and then we've got colloidal suspension. We can do our stereolithography. We end up with our composite, our green part. We put it in the oven, which is the debinding and the sintering. So first you burn off, you evaporate out the solvents, and then you burn off the organics. And then you end up with a fused silica glass, because the silica particles that were present in the nanocomposite at the high temperature, they melt and fuse together. Still again, all happening with high resolution and 3-dimensional control of your design parameters. The material is commercially available. It is expensive, but really nice. And here you can see an example of a little Eiffel Tower that was printed with it. So glass materials can be made by digital light projection. It's also possible to print flexible materials where using an air channel you can actually have droplets here. You can change the size of the droplets and then cross-link them further together. If we look at what else is happening at 3D printing, we can print with multiple colors. So we can not only have one photochemistry present in the devices, we can have complementary photochemistries taking place. Whereas if we hit the light with the blower UV, we get one cross-linking happen because we activate photoinitiator number 2. If we've got a complementary photopolymerization pathway with a second wavelength, we can actually make a different material, which means that if we've got a 1-pot resin, we can change the wavelength at which we do the printing and then combine the synthesis of 2 different materials from one resin using 2 ways of photo cross-linking that don't interfere with one another. We can also use photochromic dyes to make temporary printing masks. If we've got a material in our resin that goes from colored to optically transparent, if we don't hit it with any light, we have very poor light penetration. But if we expose the light, we get transparent areas being formed, allowing us to photo cross-link this in these areas with another material. And one of the ways that that's been used is to print at 2 different wavelengths from the same resin. And you could print firm materials that were stiff and had a glassy-like composition using both cationic polymerization and radical polymerization. If we go to the higher wavelength, then we can make this compound transparent, and therefore we're only down to radical polymerization. The cationic polymerization is no longer active because we don't have this UV synthesizer being, or there's light sensitizer being activated, and we only get a rubbery material formed. So here you can see how you could use that in printing a butterfly, where the wings need to have a relatively stiff structure. So they were printed at 470 nanometer exposure, but the joints to allow the butterfly to flap its wings, they were printed in the rubbery material, and therefore it was possible by using the photochromic effects to create transparency of the photosensitizer, to change to only radical initiated polymerization and create the flexible joints. So material science, photochemistry combined with masked light exposure to do 3D printing. In addition to having complementary chemistries like cationic polymerization and radical polymerization happening at the same time, you can also use a photo initiator and a photo inhibitor at the same time. For making these features here, a system has been used where exposure was used from the same side. So we've got the inhibiting and the exposure light hitting from the same time, and that way finer features could be created. Here again you can see that it happens under orthogonal angles, where we can have UV-based polymerization to activate the polymerization and the blue to create a photo inhibitor. And you can see that the photo inhibitor here are the tubes. You can see little holes being printed because the photo inhibitor prevented any polymerization from taking place in those lines. All of this combination is moving towards volumetric 3D printing. What we really would like to do in DLP 3D printing is to get rid of all those layers that we're working with. We would love to be able to just print in the volume without having the moving stage, because that also takes away the point that we always see the layers coming back in what we do. What we did a few years ago is to combine photo absorption and photo inhibition in order to allow for continuous 3D printing. So we got an RGB projector here exposing 470 meter light from the bottom. But for most of the time, we also had a UV projector projecting a 365 nanometer light from the side. As long as this projector was on, it didn't matter what happened from the bottom. The photo inhibitor just stopped any of the projection. But if we masked here in the side illumination, then all of a sudden we would create voxels where polymerization was allowed. So here we've got, in the first step of printing, we have the side illumination happening from the side, so no polymerization, but not on the bottom. We have our light coming in from the bottom to cross-link to resin, so we get a little device being made. During our next step of printing, without any moving parts, we had a little flag coming out of our purple projector, where you can see we leave a little void here at the side. Our light still only came from the bottom, and that allowed to make the second step. And then in the third step, we could print the roof. So here, this was masked, so here we had polymer being formed and there. Then for the we printed top from bottom, sorry, I'm telling the upside down. So the first print we printed had no light of our photo inhibitor coming from the side, so we had the polymer being formed here. Then we had the 2 bits of light coming in. So structure 1, getting the first layer formed, structure 2, getting the roof, structure 3, get the photo initiation only happening here at the bottom, and we get a 3-dimensional structure being formed by playing with the light that comes from the bottom and from the side. If we have both photo initiation and photo inhibition, we don't have any polymer being formed. If we only have photo initiation and no photo inhibition, because we've used the mask of our purple light coming from the side, we can create little voids. So again, having a good understanding of the photochemistry and see how you can work with the different hardwares allows you to move to different types of 3D printing. So in less than 10 years, 3D printing has become a normal in microfluidics. The research opportunities are in the development of new materials that allow you to get higher speed, higher resolution, or a higher level of functional integration. And it is the resin development, particularly in microfluidics, that drives a lot of the advances in digital light projection. The printers are good enough. We have the optical resolution to achieve what we can do, but it is the resin development that is at the moment the limiting step. And then there's the ways where we can minimize the oligomer polymerization by controlling the dose using the photoabsorber. And there's approach that use multi-wavelength processing in order to enable volumetric 3D printing. So they are the big things that are happening in that space at the moment. So that's all about digital light projection 3D printing. Then, in the interest of time, I'd like to move on to the fuse deposition modeling lecture. And we've already gone through the basics here. But so I'll recap what fuse deposition modeling 3D printing is, what materials are available, what kinds of transparencies we can have, and what the fluidic properties are. What I think I was talking about. Yes. So with fuse deposition modeling 3D printing, we have the filament that is a solid. We convert it into the molten version of the polymer, and it is then written onto the substrate. The FDM printer, we've got again the box sitting in. We've seen it during the lectures, and here we can see a close-up of the nozzle that has got a certain diameter that the liquid polymer is coming out.
The data is then transferred to a machine.
So that's how the process works.
The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer.
So again, we've seen that with the lecture. So FDM 3D printing, we're talking about a thermoplastic that we can buy in a spindle, or if you want to make your own nano composites, there's actually little machines that you can buy to blend your nanomaterial with a thermopolymer, mix it all together and extrude your own materials that are then available for FDM 3D printing. For microfluidics, for the materials, clear materials are perhaps the most important to be used, and PLA, PETG and polypropylene are the most suitable polymers because they have this optical transparency and allow us with FDM 3D printed devices to print transparent materials where we can actually see what's happening fluidically. We can then add functionality where there is carbon fiber doped materials available, or where there's a continuous carbon fiber strand being pulled with the pulley in combination with the thermoplastic. So you have a long carbon fiber strand in there, again providing that extra strength. And there's also FDM materials that contain metal composites that potentially could also be sintered together to remove the polymer part to end up with stainless steel like materials. We've already been through that one in detail. So looking in more clearly for the FDM printed materials. These are a couple of materials that you can just buy on Amazon or through any other online companies. The dimensional accuracy depends a little bit on the different materials, but typically we can print 200-300 micron features with an off-the-shelf printer and an off-the-shelf material. If we want to optimize our printer for better transparency, we typically want to print a little bit slower Okay.
Agitation of polymers.
Okay.
We talk later.
So typically 22, the print that we saw happening with Professor Balraj was in a black material, and we can print that at reasonably high flow rates or print speeds. However, if we print transparent materials, if we print at around 25 to 30% of the rate, the transparency of our final product is a lot better. So if you have your printer optimized for printing something in black and you get one of these transparent filaments in there, you may want to significantly reduce down your feed rate in order to get to the optimal transparency to do microfluidics. If you have some thick layers and you've got different nozzles, thick layers are better with larger nozzles. And if you want to have structures that refract the light, print at widths that are a little bit under the size of your nozzle diameter. Use the nozzle at the highest possible temperature that your material allows. The more flowy the material is when it comes out your nozzle, the more transparent your FDM printed material is. A flow rate just above 100% works better for getting nice transparent materials. And use your infill, which is one of the settings in 3D printing if you color in a section area. If there is only lines in one direction, that is typically easier, better to achieve than when you start cross-hatching. Because if you think back about the little animation that we've just seen about the 3D printing, the material is laid down on the surface as kind of sausages, and each of these sausages will have a small cavity next to them, and that will be a source of the diffraction of light and therefore less transparency. If we have a single direction for the infill, we have less different angles that can bounce the light around, and therefore we can end up with more transparent substrates. One of the nice things a group has done recently is look at optimizing the channel feature size that can be made with FDM 3D printing. And what they did was get a list of different nozzle heads. And these were not all available as nozzle heads for FDM 3D printing. They were actually nozzles that were used in an air gun, but had the same thread, the same fitting sitting on the top. So nozzles between 100 to 400 micron were used to print channels, otherwise under the same condition. And you can see it at high temperature. If that high temperature is close to the polymer starts flowing, and that can result in some deformation of the printed materials. However, if we can create a little bit of space by using a nozzle, then this hot body doesn't need to be as close to the object that we're printing, which means that the thermal disturbances on the surface are a lot less. The red and the yellow colors here means that it gets hot, you create hot spots, and that leads to the melting and the deformation of the material here. If we create this increase in space, you can see here that the substrate isn't heated as much by the radiant heat coming from the nozzle, and that allows for much more regular patterns being printed. So what was learned was we can get much more repeatable, prettier prints if we have a longer nozzle, and we can print smaller features if we've got a narrower tip. They then looked at the raster, so how you want to color in your printed subjects, and looked at the width layer, the raster width, and the layer height, and used used experimental design to find the optimized condition. So they did a couple of points in the experimental domain, got it to fit, and figured out the optimal conditions in order to print a device. And you can see here, got really nice transparent device when working on the optimized conditions, whereas under the suboptimal, the transparency wasn't as good. So here you can see a logo of 3D printed device, and you can see you get really nice transparency when working under optimized conditions. So yes, a 3D printing, FDM 3D printer is cheap, but you may need to do some optimization of your print process in order to get your high quality print. But what was achieved here by making some small accommodations for printing and microfluidics, the nozzle size as well as extending the space between the print head and the substrate, printing 100 micron channels with an FDM printer. 6-7 years ago, I wouldn't have believed it was possible. I said, "No, you can't do anything this smaller than 500 micron." So using some innovative use of elements parts engineered for other applications, you can actually get to nice thermoplastic devices. And then again, once the resolution point has been addressed, FDM has got a really rich amount of different materials available, so you can print functionally integrated devices. Talking about the digital light projection, we already talked about printing glass. The same materials can also be made by FDM printing. Again, we've got two different options there. We've got the hard glasses that have got the very high melting points, and the soft glass like sodium lime glass that have melting points that are a little bit lower. There are some ways of 3D printing in furnaces for breaking glass, as well as printing glass composites, similarly to what we looked at, the composite printing using digital light projection. There's also composites available as FDM material for printing glass. So here we've got a 3D printer that actually prints inside a furnace. So the whole area here is heated up to the melting point of glass. And you can see some optical fiber elements. So this hasn't been applied to microfluidics, but the optical fibers contain very similar cavities to what we're used to use in microfluidics. And fiber-like constructs, like here, have been made at a centimeter scale with so 7 centimeter long, and the diameters of the optical fibers that were sitting together in the hexagonal structure here were 100 to 130 micron. So I think this is one of the advances that is waiting for microfluidics to adopt. Mind you that this printer will be energy hungry and hard to operate because it's printing inside a furnace, which means that all of your elements here are sitting above 700 degrees Celsius, which typically means that oxidation and corrosion processes happen a lot faster. What I personally like better is printing the green composites and then firing them. With Glassomer, we just already looked at the resins that were available from DLP. The same idea of using these different size of silica nanoparticles was also converted into an FDM filament. And here we can see the green part that was FDM printed, where you can see the sausage-like structure where the FDM filament was deposited. You can see here a 3-layer high structure was formed. The FDM printer was stopped, so here we've got a little void, and we've got channels of decreasing size. After sintering, this looks like glass. You can see that this is a glass-like material, and it works as glass. And you can see microfluidic structures could be FDM printed, or the green part could be FDM printed. And after sintering, we've got a glass microfluidic device. What is clear with FDM 3D printing is that we deposit the material in sausages, which means that we'll get we get a highly textured surface because we've got the different materials sitting here. You can see that if the side of a channel, we get this really sculptured structure, which means that we get different fluidic properties. One of the ways this was used is use this different infill, the way of coloring in with different density of rasters. We also know that the capillary pressure of different materials changes with our pore size. So here we can see that if we change our raster, we can increase the solid fraction by getting narrower and narrower, and therefore we've got more polymer, less void. We can use this porosity to change the wetting of the material. So here we've got a material that if the material is above a certain critical length, it will be repellent, whereas if its distance is under a certain length, it will be permeable to material. So we can start using the rastering of the FDM printed devices to allow certain materials to wick into our substrate or not. So we've got the permeability model, and we can have our materials wicking in to our printed substrate at different rates. If we then have a change from one raster infill to another through a step change, so we've got an infill from 0.4, so 40% of our material, of our space is taken up by material, to 80%, our wicking rate at 0.4% of 0.4 infill is smaller than that it is at 8.8 because we have more void space, lower flow resistance. The wicking will go faster. This means that we can have two different wicking rates with our two different infills. And if we combine the materials, we can kind of slow down, control our fluidic transport by having a little break sitting in the middle. So we've got a steep slope for our low infill, a more moderate slope for our high infill product. And if we get a mixed mode of our different infills printed, where you can see on the light reflection here the different levels of infill, we can have our material being wicked at different rates in different areas, which may be convenient if we want to slow down our liquid processing because we've got a decreased reaction rate or we want another process to take place. I talked about before about the lay, but you can also use that to tune your fluidic behavior. Here we've got some microfluidic channels where the orientation that our printer prints is put differently. So at 0 degrees, our microfluidics are flowing in line with the way that we've laid down our print settings. Whereas under 60 degrees, our microfluidics is orientated, our microfluidic flow direction is orientated at 60 degrees angle compared to our lay. Here we've got a microfluidic device with two different dyes being flown next to each other when printed at 0 degrees. And you can see that, like as expected with laminar flow, we have very little mixing happening at the boundary. However, if we print at 60 degrees, you can see mixing happening because the fluid will start using the flow lines here. If we use that any further, we can have the 60 degrees at the top and the bottom of our microchannel. If we can see here that under 60 degrees we get a flow of our yellow into our blue dye because the 60 degree angle flow lines of our material lay are being followed. If we put that in opposite direction on our top, we get circulatory flow happening because of the lay, because we've got these sausages that are on a 60 degree angle that are guiding our fluid transport. We've seen before the herringbone mixers that started pushing the liquid flow up to the wall and create a mixer this way. Here we use a property of the lay of the 3D printing process to either have laminar flow or to have mixing, and then the mixing can be enhanced by having opposite direction sitting on the top and the bottom of our microchannels. So you can see that the mixing improves. If we start at the start of the microchannel, we can only see a little bit of mixing in green showing up. 5, 15, 20, 30, 40 seconds. We get better and better mixing, even though here we can see that there was no full mixing yet. But here we're looking at the bottom flow that was already well mixed. Another half a turn means that we get a look at another segment of the fluid. And here it appears it isn't fully mixed yet. So we'd expect here after a further distance the mixing to be more complete again. So fast mixing could be really good, and we use this here for coulometric determination of iron, where we could use this circular mixer to get very fast mixing of our iron and phenanthrene as a reagent, and we could achieve the color change. However, if we want to do isotachophoresis in these kind of microchannels, it is really challenging, because as soon as we get our peak focused, if we've got are in line with the microchannel, if we get to these cross-shaped, we actually mix up our separation as it's happening, and we get much uglier peaks printed under the 60-degree angles than we do get when we print our features in line. So the lesson we can learn from that is that we can do different types of chemical processing in our 3D print depending on how our 3D printing nozzle moves while we're printing our features. Sometimes we do want mixing, so we want to have that cross. Sometimes we don't, and then we probably want our fluid to go in the same direction as we lay down our material in our 3D printing process. One of the nice things about multi-material, about 3D printing with filaments, is that we've got a broad range of different materials available. There's two different ways of printing in different materials. There's multiple printers, where here you can see in one printer we've got 4 different print nozzles that each can be fed with their own material. The other option is to get your filament and fuse it together to combine different types of materials and then know what the length is that you'll be using when you will need your new material. So that requires a little bit of calculation. It's a much more waste intensive way of doing it. So, but here we've got a 4 material 3D printing that again we got a couple of years ago from Kickstarter. And our dream here was to do a multi-material print where we could combine different chemical functionalities in a device that was printed in a single step without any manual intervention. If we look at the design, the CAD drawing here, we've got the bulk of our device is printed from a transparent PLA because we want to see what's happening in our microchannel. We want to do optical detection. So that's just the bulk device material holding the channel, forming the channel, and providing the structural rigidity. You can see a couple of black different dots, and these are all conductive ABS. So they're an ABS that is filled with carbon and therefore provides electrical conductivity. In this instance, we wanted to have a functionally integrated device for electrophoretic separation. So these conductive points will become our electrodes that drive our electrokinetic sample processing and separation. We then, and it's a little bit harder to see between our green and our red channel, as well as between our red and our blue channel, we've got 2 different membrane materials. And they are FDM filaments that you can soak in water for a while to remove a water-soluble component. And by the end, you have a porous material left. We bought 2 different ones that were called lay felt and lay gel. The lay felt had a pore size of, I think it was 20, 25, maybe 30 nanometers. And we had the lay gel that had a pore size of only 1 or 2 nanometers. And we wanted to use that to make a size mobility trap that I'll talk to you later. So this is how the ultimate device looked like with all the microchannels filled with food dyes. Here we've got a close-up of the printed device where we've got our 2 electrodes with in green our sample. And in this case our sample contains some proteins, an analyte, and some salts. We'll be looking at some cation electrophoresis, so I haven't indicated any of the anions that are present. In red, we still have our separation channel. In blue, we've got a waste channel, and we have our channel with large pore size, around 25-30 nanometers sitting here. We've got our small pore size material, only 1 or 2 nanometers sitting here. If we apply a potential difference, our sodium wants to go to the negative electrode. Because sodium is a small inorganic molecule, it will move both through the large pore size and the small pore size material. So our sodium ions will end up with the waste. When we've got our analytes, they are little bit larger. Think about them as a pharmaceutical, 500 Dalton. Still fit very nicely through our large pore size membrane, but the pores in our second membrane are too small to allow our analytes to get through. So even though the electric field drives our analyte to want to go to the blue channel, the pores here form a physical barrier for the transport of that analyte. So this is what we've called a size mobility trap. The molecule here has got the mobility in the right direction to want to go, but this membrane here, by size, it is restricted not to go through to the waste channel. Lucky us, because that means that our analyte concentrates into our channel that we want to later on do our separation. Then we had some proteins present. In this instance, we were working with urine samples. Urine always has got a small bit of albumin in there. And our proteins are a lot larger than our analyte molecules, which means the proteins are too large to fit through the pores of our first membrane. So now we've got a device where we can desalt, because our sodium ions go through both membranes. We can concentrate our analytes by selectively extracting it into our separation system. And we can get rid of our proteins, because our proteins can't be introduced in our separation system because they don't fit through the first membrane. Here you can see that we've applied this to the analysis of ampicillin from urine samples. Ampicillin is an antibiotic. And we can see that if we follow the sample preparation that I just detailed up with an electrophoretic separation down into the bottom of the slide, we can have a fluorescence detector sitting at the end of the channel. We've got a transparent material, transparent ABS that we printed this in, and we can measure the fluorescence intensity. We used a fluorophore that was amine selective, so there are some other small molecule interferences that also have amines in there, so we could separate them away from our target ampicillin using our electrophoretic processing, and therefore we could quantify the amount of ampicillin that was present. Here we see a blank sample that didn't have any of the antibiotic ampicillin in. We can still see a couple of other cations that were labeled, but because they were resolved from our analyte peak, we could quantify the amount of ampicillin that was present in the urine, doing all the sample processing, doing both the purification and the concentration inside our functionally integrated microfluidic device. So while FDM may be often overlooked due to the poor resolution, advances have enabled FDM printing down to 50 micron channels. So I showed you the 130 micron channels when talking about these guys that work with a nozzle. They were able to improve the resolution there from 130 down to 50 using the distancing. The lay of the FDM printing allows for fluidic control. So you need to know what your fluidic behavior is that you want to have in a certain section and play around with the way that the nozzle lays down the material. The amount of materials that are available is mind-boggling. So if you've got any application that needs a special material, there are a lot of different choices that you have, covering composites, so normal polymers, composites, glass-like material. And then there's also options for multi-material printing, where you can either splice, you can combine different materials together and calculate how long you need to have your thread being pulled through your FDM nozzle to move from one material to another. And there are multi-material printers that allow you to combine different materials in the single print as well. So that is the information that I had about FDM 3D printing. That should bring us to lunch. I'm happy to answer any questions if you have about 3D printing, and then I'll have a quick look at Professor Malik because he just said that the program for this afternoon has been cancelled.